I'd like to spend a little bit of time talking about the problem of space debris. Now, I kind of pinched this title from a planetarium in Philadelphia. Had this as their talk. This was about 30 years ago when I saw it. I was like, this is a great kind of catch-all topic about what it is that we are doing when we go into when we go into space. And so, of course, a word of thanks to I guess several different organizations. My organization for letting me come to Australia, Missouri S&T, Missouri. I don't know how many have been to the U.S. Probably several of you. I mean, in the line of duty, as it were, right? So you probably know that Missouri is in the middle of the country. We're kind of like Chicago's up here, Texas is down here, Missouri is right in the middle. Very green, lots of rivers, very nice, very nice state to be in. So I'm with the Missouri University of Science and Technology, which is about 8,000 students. So we're a relatively small institution, heavily focused on engineering and sciences. The Fulbright Commission, of course, is what allowed me to come here to Australia to begin with and participate in these activities. The DST group, as it's letting me come and visit with you all for an afternoon or so. And of course, thank you to Michael and you all for being here and for facilitating this event. It's good to be here and visit with you. I tend to look at things kind of simply, okay? So there's stuff in space, okay? Right, there's lots of stuff in space. So there's useful stuff. That's what you do to watch Netflix or call for a pizza or whatever. Those are satellites that are still doing something useful, all right? Then there's the stuff that's not very useful, okay? So we're gonna talk a little bit about both of these things, maybe start off by talking about some of the useful things that are out there, just to kind of set the context for the other stuff. Being a professor, though, it's time for a pop quiz. Let's see how smart you guys are. What was the first Earth-orbiting satellite? Okay, I'm not gonna. I do this in my class. I don't know your names. I don't know your handwriting. So go ahead and shout it out. Sputnik, Sputnik, Sputnik. Okay. Trick quiz. Trick question. I know. But yes, you're right. So Sputnik, of course, the first human-made, man-made satellite, followed shortly thereafter by the Explorer satellite that the U.S. launched, and since then there have been lots of satellites launched by lots of different countries. There's a couple in the 50s, 60s, 70s, and a whole bunch more came here in the 1980s. You all launched something for the UK a couple of decades ago. You have a new space agency now, very exciting, getting back into the business of space. I think that's great. But it's a relatively small community of what you might call spacefaring nations. Okay, so there hasn't been a lot of activity until recently. The useful stuff, where is all this useful stuff? Well, about half of it is in what we call low Earth orbit. Okay, that's this was shuttle went, the space station is, a Hubble Space Telescope is there. I'm talking about the major U.S. project, Soyuz, Salyut from the Russians. And then there's a lot of stuff in GeoSync. That's 20,000 miles up there. That's where the telecommunications satellites are and all the other stuff. It's going a little slower. The stuff around in LEO is whizzing around pretty quickly. That's where most of the stuff is. What is all this stuff doing? Well, if you take a look at, if you add the percentages of, let's see, this one, it's 11 and 38 and 9, you get pretty close to just shy of 2/3 of the satellites that are up there that are doing useful things is to facilitate communications, to allow people to talk to each other for whatever purpose you have. Most of the stuff that's up there is to facilitate communications. Some of it's for research. There's military stuff going on, weather forecasting, science, technology demonstration. Whether or not we're actually going to see some technology demonstration later today in the show. But this is kind of just a rough estimate of what was up there until a few years ago. Right. So this was fine up until about 10 years ago. Okay. Now we'll see how old you guys are. Then along came the new kids on the block. No? Yeah. Vinny, Nick, something. I don't know who it, but no, not that boy band, but the New Kids on the Block about 10 years ago, several companies started putting forth this crazy idea. Back then it was considered crazy, now it's like, well, yeah, that kind of makes sense. These companies are putting out what we call large satellite constellation, mega satellite constellations, thousands and thousands of satellites. You know, there are maybe, I don't know, several hundred satellites up there right now that are still working, maybe several thousand. But these groups are planning to put up, if you take a look at some of these numbers, some of them are staggering. Boeing, about 3,000 satellites. OneWeb, in fact, OneWeb just launched about a month ago, my buddy was telling me, the first bunch of satellites. The Chinese are getting into business with several hundred satellites. Samsung. SpaceX, now you keep hearing about Elon's money troubles in my Google feed, so I don't know how far he's going to go, but I think he's launching 60 satellites already, I think, this week. So he's planning on 12,000 satellites up there, okay, to have these constellations. Now, constellations are really nothing really new. We have Iridium that's up there. There are a couple of other constellations that are 60-ish, but these are intended to cover the globe with these little satellites. Now, little, they may be, you know, the size of this desk or podium or something. They're not that little, but. And there's a good reason for doing this. There are several good reasons for putting up these satellite constellations. World Wide Web, as fast as it is, however, 10, 20, 50, 100, 200 mega, whatever you're getting per second, yeah, that's fast. It can be faster, okay, if it doesn't have to deal with atmospheres and bouncing around and all that kind of stuff. The reality is that the internet is not available everywhere. The internet has knowledge. The internet has useful knowledge, if you could ignore all the other stuff. The internet does have some useful information that is important to get to people. And right now it's not possible to reach them. So having a Skynet, if you will, might help. And disaster management. Not every planetary disaster event needs the same kind of eyes, if you will. Fires are different than floods, which are different than hurricanes, which are different than tornadoes. So different kind of disasters require different kind of eyes to see them. And so having this kind of distributed network will come in handy. There is, of course, the downside. There's no such thing as a free lunch, right? The possibility now exists that, wow, we're putting a lot of mass in orbit. And so the possibility is going to increase that A, it might hit each other, or B, it could get hit by another stray piece of space junk that's up there. Astronomers have to be really mindful, or anybody that does visual or infrared or other observations or keeping track of stuff that's up there are going to have to be really mindful of stuff moving across there, if you want to call it glass plates or vision or field of view or whatever. They have to know exactly where it is, so they have to keep track of a lot more stuff. Right now we get close approach warnings. NORAD doesn't tell you what to do, but NORAD can and will let two satellite operators know, you know, hey, based on this TLE and that, you guys are going to be about 100 kilometers apart. What are you going to do about it? Do you want to do it? It's up to you guys to do anything, but we're just telling you that we have this close approach. You figure out what you want to do. It's going to be a lot more of those close approach warnings now. So there's going to have to be a lot more quick decisions about what to do. All right? So there is a cost to this good thing that we're having built for us. That leads me into, I guess, the meat of the presentation, which is orbital debris, stuff in space that's not really useful. Okay, and just like anybody who's solving a problem, who wants to know a little bit more about their problem, the kind of questions that you're going to ask are very similar to these, whether it's in space or whether it's on Earth. Okay, there's all this junk. I need to know about where it came from. How much of it is out there? What can happen if I mess with it or if it touches me? Can I prevent that from happening? Can I protect myself, and how? And will this problem get any better or any worse? Do I have to actually actively clean it up, or will it take care of itself? Okay, so very similar questions that we're going to answer hopefully by the time this hour or so is done. Space debris is becoming more and more of a popular item, if you will. There are more and more headlines. I keep track of some of the blogs and news feeds I get. Back when we were flying shuttles, we always have something come up about astronauts having to dodge a piece of debris or shuttle having to move out of the way. Stuff comes down, stuff falls down. So we've had experiences where we had to watch out for satellites that have re-entered, space stations. So you see these kind of headlines appearing every now and again, depending on what you subscribe to. And then of course when something does actually happen, there is news and there is a discussion about how bad is it, how good is it. Who's seen the movie Gravity? Don't be embarrassed. You can admit it. That's okay. I know. The physics is, but it was a really cool movie. All right. Okay, come on, guys. It was a really cool movie from a movie perspective. All right, check your intelligence at the door. Okay, that's fine. Enjoy the movie for the movie. Sandra Bullock's hair is not going to look that good in real life. I understand that, but the reality is that it opened up the eyes of a huge audience to the problem of space debris. Okay, which is wow, what a great public awareness campaign. All right, I thought it was really cool. And like I said, if you ignore the physics, some of the stuff that happened there is not that far from reality. You could have a cascade of impacts. You could have a space shuttle destroyed, maybe not all at once in a single hit like that, but this is not outside the realm of possibility. Now you're working in a cool area when you're thumbing through your 6, 7, 8-year-old, I don't know how old he was. We have these book sales, scholastic book sales for your kids. You probably have them here too. And you're thumbing through the book. Oh, stuff on space. Yeah, okay, I'll look through those books. And I'm thumbing through. Oh, bigger spaceships. Oh, okay, I'll see what's in there. On page 16, there's a paragraph on space debris. This is really cool. So that stuff that I'm working on is being brought down to children of 5, 6, 7, 8 years old. And if you play games, I need my son up here to tell me which game this is. But this is from one of those role-playing space first-person shooter games, I guess. I don't know, where they talk about Earth. It takes place in space. For detailed information, please refer to the Standard Issue Alliance Galactic Codex. Earth's orbit is riddled with debris generated by bootstrap space development. Use of kinetic barriers is recommended at altitudes over 85 kilometers or whatever. So this is really cool. They didn't have to do this. They didn't have to put anything about space debris. But the fact that somebody, when they were building this program, tried to make it more, real, interesting, gave it a twist, talk about space debris. I thought that was pretty cool. Well, why do we have space debris? Well, I guess people are people. No matter what we do, no matter where we go, we always leave a little bit of something behind us. Now, I'm looking at the floor here, and this is immaculate. Okay, this is amazing. As I walk around the grounds, this is like spick and span. This is clean. Okay, but maybe if you go outside, or if you could come to the U.S., you'll see that sometimes we have little wrappers, a little soda can. There's a sneaker somewhere on the side of the road, plastic bags. It's part of it's how we do business. It's how we are. We drop things. There was a mission not too long ago where an astronaut forgot to tie down a toolkit, and it flew off. So now there's this expensive toolkit in Earth orbit somewhere, okay? So accidents happen. We forget about things. We also have different kinds of accidents. You build spacecraft, you get them up there, fill up the canisters with fuel and power and batteries, and just like anybody else, you fill up your gas tank, squeeze, you always put a little bit more than you really need, just in case, because until you get there, you don't really know how far away it is, and how much fuel you're gonna need, how much battery power you need, so you always add a little bit more. Well, when you're done with your mission, you have all this fuel and stored energy still flying around. If it gets hit, that's just gonna cause a whole bunch of debris to happen instantaneously, okay? Possibly. So the way we build our spacecraft sometimes lends itself to debris generation. We had a wake-up call about 10 years ago when Cosmos booster hit an Iridium satellite. One of those constellation satellites. I think there are 60 some out of those satellites. Now, redundancy is always usually a good thing, so we had a couple of extra Iridium satellites. When that one was lost, we put another one in, and all the communications continued as per normal. But this caught everybody off guard. It's like, where did that come from? How come we didn't see that happening? Really? An old booster hit a functioning satellite. And there have been other orbital mishaps, as I call them. You can be a little generous and call them mishaps. Some of them are accidental, okay? And that's because we just don't, and sometimes we just don't know why. Some of them have been intentional disruptions, and when those happen, those are, well, not very helpful, to put it simply. When we had one of our spacefaring nations, as I mentioned, recently conduct an anti-satellite test. Every country is allowed to chart its own destiny and to do what it deems is appropriate for what it wants to do in its mission and goals as it sees itself. But there are consequences, okay? And so when you do an anti-satellite test, you put astronauts in harm's way, okay? And things, I guess I didn't hear anything catastrophic happening, so I guess things worked out okay, but for a few weeks there, it was really nervy. And, it's just one of those things you just have to watch out for. What kind of stuff is up there besides a booster and a satellite? Well, you got all kinds of stuff up there. I mean, you have the big stuff that's boosters. You got mission-related debris like toolkits and panels that fall off that are typically maybe 10 centimeters. You have rocket fuel effluent. You have paint flakes, meteoroids, naturally occurring things, pieces of thermal insulation. Stuff degrades in space from atomic oxygen erosion, what we call it, okay? I mean, that stuff's nasty. That just eats away at whatever surface is up there if it's susceptible. So you got a lot of things up there, different sizes, lots of different pieces. I kind of put this up there just so for my own benefit, just so that I can bring it home to a little bit of how big these things are. I mean, when I talk about boosters, you kind of can imagine a booster is like a school bus, okay? It's this big thing, okay? We all know what a booster maybe looks like. But this stuff, okay, so we have baseball, you all have cricket here, right? But I think the ball is roughly about the same size, right? It's about like this, right? So this is about what a baseball size is, 2-3 centimeters here. About 10 centimeters in diameter, maybe less, maybe 8. This is maybe a grain of sand or a tiny pebble that kind of puts it into perspective. But this is a marble. That's about 1 centimeter like that. And depending on what hits it and where it hits it, different things can happen. How has this population been growing? Well, quickly. All right. Visually, this is a very popular graphic. Now, this is obviously not to scale because some of these dots are like the size of a big city. So obviously, these dots aren't true to scale. But it gives you an image it gives you growth, perspective on growth. That it just initially we started out with some geo, mostly low Earth orbit. As we got more and more into polar orbit, we got more and more stuff going in different directions. But there's a big geo ring. There's obviously a big LEO ring. So it's been growing, well, kind of almost by leaps and bounds. From the early 60s to maybe about 5 years ago, it's been a pretty steady growth. You have some explosions, whether they're intentional or not. This is the anti-satellite test from the Chinese about in 2007. This created, let's see, this before then it was around 11,000. That's the number. When I was doing a lot of my work in the 90s, the number that I was familiar with was between 8,000 and 10,000 pieces. And then this satellite happened, and that brought in, it went up from 11 to about 15. So that's 4,000 trackable pieces. The iridium explosion, collision went from 15 to 17, so that brought in 2,000 trackable pieces. What's a trackable piece? Trackable piece is basically fist size and larger. That is tracked by NORAD and other, you all are developing an awesome SSA capability here, have one already. Other countries are developing this capability. NORAD is ours. NORAD, besides keeping track of where Santa Claus is on Christmas Eve, also keeps track of space debris, and so it tells us where it is. What happens when so now we know a little bit about where it comes from, why it's up there, how much of it is up there. What happens when you interact with a piece of space debris? Well, my students hate this. I got one review at the end of a semester. Dr. Schoenberg would be a better politician than a professor. And I was like, well, yeah, okay. That could be fun. You all had an election recently, so politics might be a little bit right now, but that's another story. And the answer, what happens when this piece of space debris hits you? Well, it depends. It depends what kind of spacecraft you have. It depends where it hit you, and it depends what hit you. Okay. If you were hit by a piece of sand, a millimeter in diameter, not too much is going to happen. That's probably be small hole, small crater. You get hit by something larger, you could lose a solar panel, you could lose a radiator. May not end your mission, but might put you into a different kind of mode of operation. If you get hit by something bigger, yeah, you could actually lose a space station module, seal it up, and get out of it as quickly as possible. And then, of course, if you get hit by something big, then you could just lose the entire spacecraft. The only interesting thing here is, if you're a space telescope or some other optical or infrared or some other tracking device, and you happen to be looking right down the barrel of a piece of space debris that's coming at you, and it hits you, it could be a piece of sand. Will knock out the lens, and now what you have is a $2 billion paperweight floating in outer space that's useless. Okay? So it doesn't mean that you need to get hit by something big to lose what you have. You can get hit by something little and lose functionality of what you have, rendering what you have totally useless. All right? So how do we learn about what happens when a satellite gets hit by a piece of space debris? Well, we're not actually up there holding a satellite yet and watching for it to get hit, so we have to do something here on Earth to test what would happen if a satellite were to get hit. So a couple of decades ago, there was a socket test by the Air Force, kind of this made-up satellite with some funnely things and cylinders and round and cone things. It hit. It was hit with a pretty substantial projectile, and the pieces then were collected, categorized, shape, size, density distribution, and that gave rise to the standard breakup model that a lot of agencies and a lot of folks, perhaps even you, are looking at using to predict what happens if a satellite were to get hit. Okay, the fragment size distribution and all that kind of good stuff. About 5 years ago, the U.S. and Japan worked together to do a similar kind of a test. Only you can tell by it was a box with lots of stuff inside, and you can tell by the fragments as they were categorized that this was a sufficiently higher fidelity satellite with lots of other different kinds of pieces and parts and all kinds of different things in there that made it a little bit more realistic. So we upgraded our standard breakup model. And just recently, NASA conducted an impact of what looks like a much better pretend satellite. It's got solar arrays, it's got MLI, it's got gold and silver and solar panels and all kinds of instruments and everything what you would expect a satellite to have. Made out of composite materials that we would see in satellites now more and more and more. And there is a team of graduate students working feverishly in the University of Florida. I think the goal is to categorize 500,000 fragments, and they're up to like 300,000. I mean, how many of you were graduate students, right? You thought you were abused. These guys, they're picking up things and they're marking them and they're weighing them and they're measuring hundreds of thousands of these little pieces. Okay, so this is very meticulous, precise work that is hoping to even extend the standard breakup model even further. Why does this happen? Why is there such a destruction going on? If you do a quick back of the envelope math kind of calculation, if you let's say have a satellite in low Earth orbit, that's a couple of hundred miles above the Earth. The radius, 2 pi r is the diameter. Low Earth orbit, it takes about an hour and a half to go around, right? Something like that. So if you divide that 2 pi r by the hour and a half, you come up with orbital velocity there is about 8 kilometers a second. So that means that if the debris is coming at you at 8 kilometers per second, you're coming at 8 kilometers per second, you can have 16 kilometers a second closing velocity. That's fast. Okay? So that is a lot of energy getting dumped. Now, I often get the question, well, aren't you all going around the same orbit? Because if we launch from the Cape, then you're going around this way, and if you break up, then you're going around this way anyway, right? So aren't you just chasing your own debris? I mean, how can you possibly hit it, right? Well, something called orbital mechanics comes into play. Space is not empty, space is full of space. And so particles that start going around this way will eventually precess and end up coming at you this way. All right, so just because you started going that way doesn't mean, and you can actually see those same particles coming towards you in several orbits, okay? So that's why that damage is so severe. This is traveling at such speeds that the energy is dumped into a system. It doesn't have anywhere to go, so it starts to melt, fragment, vaporize everything and anything that's in its path, okay? And then whatever energy happens to get out, it's got to be absorbed by the surrounding components, rivets, bolts, composite, circuit boards, whatever, and eventually those just get blown all the heck also. We see these things happening when we do, not really a tabletop test, but it's a laboratory test with a high-speed launcher. This is a multi-plate system. Their plates are at 45 degrees. There's a projectile coming in from the right, hitting it at 45 degrees. There's a bubble of debris, kind of like almost in the same path. There's a ricochet debris cloud, and then eventually this debris cloud hits the second plate, and it kind of bounces off, and sometimes stuff comes through here. But you can actually see these things happen so that there's just all these fragments and molten material just flies off. We launch these projectiles in what we call a light gas gun. They're not really light gas guns because there's not a trigger, but they shoot something really fast, so we call them gas, so we call them guns. They fire these, it's actually kind of that's really clever, soft launch capability. Imagine firing something this fast and calling it a soft launch capability. How do you get something going that fast? Well, if you think about it, speed's not really the issue. I mean, you can get a particle going at 100 kilometers a second. That's easy. That's called a Van de Graaff generator, okay? But what you just traded speed, you just traded mass for speed. The things that you're launching are really these teeny tiny little things. So we don't really use that because you can't get a lot of engineering information out of it. We're looking for size, we're looking for mass and speed at the same time. So that's why we can only go as fast as 7 or 8 kilometers a second. There's a huge explosion. A piston gets launched. It compresses very light gas in a tube. Then that gas gets compressed. Eventually, there's a burst disc at one end, and it's scored. Okay, there's a little X in there. There's a little thin region, so that when the pressure is high enough, it bursts open, and that gentle of that compressed gas is what launches the sabot and the projectile down the tube to eventually hit the target. So it's actually a very clever, very sophisticated device. They're long. They're easily 100 feet long. It's a very amazing thing when you actually see it work. So how are we doing in space? We have all this debris. Okay, so now we know, what do we know? We know a little bit about where it comes from, how much of it is out there, how do we learn about what can happen if we mess with it? Now let's see, well, what happened, what about the real stuff that's up there? What can happen if somebody touches it or if it hits a space telescope, for example? Well, yeah, we do these surveys. And NASA does a survey of the Space Telescope every dozen years or so, every few years. And it's not a question of if you put a spacecraft up, will I get hit? The answer to that is yes. There's a 100% probability you will get hit by a piece of space debris, no matter what you put up there. The question is, how bad is it going to be? Okay? So more often than not, sometimes, usually, it's not that bad. We have not. There's a few spacecraft anomalies out there that we're not really sure. And then, of course, iridium happened and all that. So, we are starting to lose spacecraft because of space debris impact. We have not lost a life yet due to a space debris impact, but we have lost spacecraft due to space debris impact. If you're an astronaut, if you're going to be an astronaut, more power to you. It's scary stuff because the soft, flexible suits that astronauts wear can be penetrated by a very small piece of debris, millimeter size. And that's a bad day when that happens. So that's just something to think about. So now that we know that we need to be a little bit afraid about this, how are we going to protect ourselves against impact by debris? I mean, after all, we are going into space. We're not going to not go into space all of a sudden because of something that might happen to us. Human beings are not like that. So the question is, what should we do about protecting ourselves? Well, the answer to that question is, it depends, okay? All right, so it depends. What are we protecting? We're protecting the International Space Station that has humans inside, your friends, your family, your mom, your dad, your sister, your brother. You're probably going to want to spend a lot of money protecting that thing, okay? How about a satellite that's in GEO? Well, I don't know, 500 million bucks? Yeah, between friends, what's a couple of $100 million, right? You lose a satellite, take out a loan, put up another satellite, right? So you're going to spend some energy trying to avoid bad things from happening, but you're probably not going to spend quite as much money on it, all right? It's just budgets are budgets. So we should protect some of our spacecraft. We should be intelligent about how we design all of our spacecraft, but the more valuable space assets should be protected. How are we going to protect our spacecraft? Come on, you know the answer. There you go. All right, somebody's awake. Excellent, good. It depends. How are you going to protect it? Not all protection methods work equally well against the entire range of debris threat, okay? There are three basic ways of protection: active, operational, and passive, okay? Talk a little bit about these guys here. Active is, as you can imagine what it might imply. Active means doing something, being proactive, hitting it with a laser. Okay, pop quiz. What's the problem with hitting a large piece of debris with a laser? More debris, that's exactly right. Okay, so may not actually work all the time. Not only that, but you have to have a really good idea where you're pointing. You know, point and shoot, yeah, that works, but you got to know exactly what you're pointing at. And our error bars about our debris parameter or orbit parameters could use a little bit of help, okay? That's not to say that somebody's not going to try. Space station could get laser cannon. Not only laser, but laser cannon. That's going to be some humdinger of a laser, that's all I got to say, okay? Laser cannon. We don't mess around, okay, you know. Whew, okay, that could be scary. Yeah, sensors got to be really, really good. You got to have a really good catalog. You got to know where everything is. Collision avoidance is another way. That's called getting out of the way, all right? And shuttle, when it flew, space station all the time now, kind of has to do a burn to sort of move out of the way just a little bit to let something go by. And it does that. You will do that. There's only so much that you can do getting things out of your way that's big and bulky like a space station. Moving something like with flimsy attachments like what the space station had, even though you're in space and space is empty, right? Space is full of stuff, so even then when you move mass in space, you're still going to have forces created. You're still you can only get away with that so many times, okay? So operational protection then says, okay, if we can't actively destroy the stuff that's in front of us, let's see if we can at least protect ourselves by working smart in space, okay? So if you know you have a sensitive element like a window, don't fly windows forward. Half the time when the shuttle was in orbit, it flew with its main engines forward, upside down, because that way, if something hit it, debris is going to hit you straight on. It's not going to come from the top. It's not going to come straight down from the bottom. It'll be at an angle. There's a little wedge angle there. There's a wedge angle here. But more often than not, it's going to come at you this way. Space shuttle didn't need the engines anymore. Once they were up there, they were done. So if one of the space shuttle main engines got hit and destroyed, well, that would be bad because we lost a few $1 million. But it's not like hitting it in the window that would get destroyed, cause a leak, and lose life. Okay, so you fly intelligently, and then you might be able to save some you might be able to save your cargo, your life, your humans that are in there. If you think about when you go back and you take a look at how you sleep, I know I know when I was growing up, I always wanted to sleep in the corner, by the window, by the wall, because it was really hot where I was growing up. My parents didn't believe in air conditioning, so in the summer I would just try to, squeak out whatever breath came in through the window. Which is maybe what some of you are used to, sleeping by the window or whatever. Now imagine sleeping. Do you want to sleep next to the wall in the space station? You don't want to do that. Now, but until somebody tells you that, it's like, oh well, yeah, I didn't even think about that. So when you're sleeping on a spacecraft, you want to sleep away from the windows, away from the walls, because if something were to come through, you kind of want to be a little bit further away from that, right? So that's called living smart, working smart in space. And passive protection is the one that is where I've made is where I spent a lot of my time working. It's basically shielding. Okay, shielding is something you put up. It's called passive because, like the bumpers on your car, you carry them with them. You carry them with you wherever you go. Nobody needs nobody needs life insurance until they need life insurance, right? Well, nobody needs a bumper until they need a bumper, and you're happy you have one. Okay, so bumpers are put out. It's very similar to the ship hull construction, two walls, like we saw in the movie stills. They were implemented in the 50s with some of the early, obviously in the late 50s when some of the early satellites went up. They were used on Apollo, Skylab, space station uses them extensively. It was it was the first, one of the first major programs that was built with a purpose-built shield. Skylab had actually a meteoroid shield. And shuttle was not built with a shield, so shuttle was very susceptible to being hit by debris, and you had to be really clever about how you flew the shuttle for that reason. We protect the space station by putting shielding in these red zones. This is, flight direction is this way, so remember the debris are going to come this way, and it's all the exposed elements then that need the shielding. What do we do with this information? Okay, so we're going to put shielding up there. We're going to develop these shields. How do we know how much shielding we need? How do we know where to put it? Well, it's a several-step process. NASA uses a program called Bumper to calculate risk. Okay, Bumper provides a point estimate of risk for a certain mission profile. That information is based on the thing that you're sending up, the debris environment that's surrounding. NASA works its during the flight readiness review. It takes a spacecraft through every orientation angle as it goes around the Earth, through every single orbit, every single day, and then calculates what's the likelihood of getting hit. Then it takes information about how the structures that are on that spacecraft respond to being hit, because we know we're going to get hit. It's just how badly the damage is going to be. We put all those together, and then we come up with these hot zones where we have to make sure that we have adequate protection. How safe is, for example, the space station? Well, times change, materials change, elements are added, timelines are extended. Our awareness and our knowledge of the debris environment changes. So things are changing all the time. The goal was over a 30-year time period to have a 80% probability of no penetration. That means no hole. The reality is that it's about a 63% probability again, because our information changes, our knowledge changes. The probability of no loss of crew, PN lock, was designed, that was a really high number. 95% was the goal. Right now it's around 88%. Okay? Now, we see these numbers and we say to ourselves, well, we got to fix these numbers. So what do? We fix them. We fix the space station. We add shielding. This was analyzed as found to be a particular sensitive part of one of the modules. And so what we did is we put aluminum plates on the outside. We added additional shielding where it was needed most. So the benefit of having this information is you can then, after launch, go up there, fix it, add some protection. The space station gets hit all the time. All right, again, it's not a question of if, it's where and when. And sometimes the where and when it hits you where you least expect it. Just like you see the pilots checking out their planes when they land, make sure everything's okay, no big deal, everything's cool. Space shuttle, same way. Astronauts walk around the shuttle, look for damage, look at the tiles, see the thing, oh yeah, oh that's, okay, they look it around. Space suits are treated the same way. Suits come home, suits get analyzed, and the darndest thing, the gloves that these astronauts are wearing had tears in them. Now, not like tears all the way through, but the fingers had like loose threads, loose torn holes, little weird things. Where'd that come from? It's one of these questions you guys get yourself. Well, some clever engineer figured out that, okay, how does an astronaut walk? Well, you and I used to walk like this, right? We walk, right? Can't do that in space. Okay? Not yet, anyway. How does an astronaut walk? Well, they go outside, they tether themselves, they tie themselves up, and then they do the crab walk. They got their feet down here somewhere, and the module's in front of them here. They got a handrail here. They hold on. Right, okay. And so that's that's how they walk. Well, the handrails, when a handrail gets hit by a piece of debris, there's a crater. And if you've ever seen a crater on a piece of metal, you know that the edges are really jagged. And so when they did that crab walk thing, rip, every time they came across a crater, they just ripped it a little bit more. Who knew? Okay, so shielding works because we take advantage of what happens in a really, really high-speed impact. The energy is dumped so quickly, it doesn't have time to heat that builds up, doesn't have time to leave, so it melts, vaporizes, et cetera, creates a debris cloud that then is a much more dispersed loading on the second plate. And so dispersed loading is a lot better than a point load, and so the second plate survives. How do we characterize the response of a shield? Is called the ballistic limit equation. And its picture, which you see here, is a ballistic limit curve. The idea is that you want all your holes, all your solids, in this case above, all your hollows, your non-perforations below. You draw a line through them, which looks really weird when you think about it. Because if you think about it, if you just had a single panel, and you held that panel thickness fixed, as you increase the speed of whatever you're shooting at it, to make a hole in there, as you keep increasing velocity faster, you'd need a smaller and smaller thing, all right? Because you'd be shooting it faster and faster. So you're used to thinking of something that, as I keep increasing the velocity, I'm going to need a smaller and smaller thing to make a hole in it. Okay, well, that kind of makes sense, which is what this first part of the curve does. As I increase the velocity, I need a smaller and smaller and smaller diameter to make a hole in my shield. Well, what the heck does this mean? This means that I increase the velocity, I can get away with a larger projectile and not make a hole? How does that work? Well, again, we take advantage of the physics that goes on, and because it hits it so fast, it fragments, it melts, and whatever, it disperses, that buys you a little bit of protection. So you can get away with hitting it with something bigger, even though you're hitting it faster if you hit it fast enough. Now, eventually, physics will take in, and you're dumping such a huge amount of energy on the second wall that you can get away with a small projectile. So this is the world that I work in, characterizing, developing these ballistic limit equations. This is a typical bucket shape of a Whipple shield, if you will, if you see those words around. Then, okay. So maybe we'll wrap things up a little bit here then with the future. If I have my crystal ball, what happens to the future? Well, does this stuff ever fall to Earth? Okay. I won't say all the time, but yes, it does. Okay. Now, the Earth is sufficiently empty so that when most of it falls down, nobody knows. because we have a lot of oceans. Okay, we also have a lot of uninhabited land, a lot of desert, so we don't often see the things when they fall down. I have to smile when I say that because Skylab fell down here. Thank you very much. You know, I think you guys gave us a $400 bill for littering. I think you fined us. I think, you know. I think somebody paid it off. There was like this radio campaign in Berkeley to collect enough money to pay it off or something, right? Yeah, that's pretty funny. Good on you. That's good. Big stuff is going to survive more than the small stuff. Okay, so when something falls down and you see it, it's probably going to be pretty big. All right. So far, only one person has gotten hit by a falling piece of debris. It was like one of like a screen or something or whatever. She got hit on her shoulder or something. Lots of cars have been hit. All the, you know, but only one person. She was okay. So you know, so far so good. So the question is, what's the future look like? Is it going to get better or is it going to get worse? Well, this was about 10 years ago. Based on the fragmentations that have happened, and we're looking way out far into the future. You know, it's going to keep growing. We can maybe slow the growth if we're clever about what we do, but because if we keep going into space, the reality is just our presence there will make the debris keep growing. Okay. We thought we had it under control. But then this anti-satellite, this ASAT, the Chinese ASAT test happened here, and that is just adding a whole bunch of uncertainty. We have no idea exactly what's going to happen. But again, because just by very nature of our presence there, it's going to keep growing. So what can we do to fix this problem? As caretakers of the environment, whether it's here on Earth or whether it's in space, what can we do to fix this problem? Well, we cannot test satellites in space anymore. Now I know we've done it before ourselves, so it's kind of hard for me to, you know, talk about this from a perfect perspective. But the reality is that when you do that now, you put others in danger. Okay. We can improve how we build our spacecraft. We can make them with not 2 times the amount of fuel we need, with not twice the battery power we need, just in case. We can be a little bit more intelligent about how we design our spacecraft. We can, and then when we're done with them, passivate them when we're done with them. Bleed the fuel out, disconnect whatever power cables you have to reduce the potential of the stored energy from causing future harm. Can we clean up debris? Well, yeah, maybe. Mother Nature doesn't help us in this one. Solar heating, 11 years, the solar cycle, the atmosphere expands, right? So the higher the atmosphere goes, the more stuff it's going to sweep down along with it. It's called friction. The downside is the atmosphere does not expand high enough. So can't rely on natural processes. So we got to do it ourselves. The concern is that you might have this thing called the Kessler syndrome kicking in, where it's just like a nuclear reaction. You have a critical mass of debris, one debris hits it, and then boom, you have this chain reaction, and you have a cloud of debris surrounding the Earth. Okay. If you've ever seen any movies, you saw it, or maybe your kids are watching it, or WALL-E, the movie WALL-E, the Disney movie WALL-E, they fly through and back in through space, the whole big cloud of space debris. It was really cool, space debris in the movies. It was exciting. So we have to clean up after ourselves. Now, I'm going to ask the question. Answers are up there. You know, there's big stuff and there's little stuff out there. So the question is, should we go after the big stuff or should we go after the little stuff? Now, both have advantages and both have disadvantages. Big stuff might be harder to get, might be easier stuff might be easier to get, aerogel, all this kind of stuff. You can trap it, vacuum it, hoover it, whatever. But the reality is that if you really want to worry about keeping the environment down, you got to go after the big stuff. Because you could spend millions of dollars cleaning up thousands and millions of pieces of space debris, and 10 years doing it, and then 2 boosters hit. It just undid what you just spent all your money doing. So the reality is, you got to go after the big stuff. Okay, that's harder, but that's where you got to go. Now, there's lots of great ideas. The problem with going after the big stuff is that we know the physics. That's pretty easy. All right, whether you're pushing it out of the way with a soft laser or whether you're grappling it or whatever, the physics is really easy. Well, it's really easy, but we know the physics. Okay, but it's the engineering and the going and doing. That's the hard part. Okay, and until recently, it's been a lot of paper studies, but recently the European Space Agency put up a satellite that has 3 experiments on it to actively remove debris. Okay, there was a net capture, harpoon, and a sail, solar sail deorbit device, and they did 2 of them. They demonstrated 2 of them, and if everything works here, this should show the harpoon experiment. Here we go. Let's see if that works. So yes, I see action. You see motion, right? Okay, good. You can read for yourself what's going on, but this is boom extended with the target. The idea is, if you can shoot a target in space, if you can target it well enough, you could attach a piece of string to it, tether it, and then bring it in, and then bring it down, okay? Or send it down. You can do something with it, okay? Now, this is kind of scary. This is exciting from a civilian perspective that I can finally go up there and clean up this junk. But from a military perspective, I can see how this can be a little scary. So, there's 2 sides to that story. The net experiment, the net experiment, this is like a couple of seconds to,
1, 0.
I can hear it on this, you may not be able to hear the sound, that's okay, don't worry about it. But basically there was an experiment, this experiment was launched, it was attached.
Capture confirmed, capture coming, was right on time.
Can you guys in the back hear this? You can, really? Okay, so maybe the next one might work. Okay, cool. So that's a scale, give you some scale. It's a box about this big, and there in each side had an experiment on it, and there's a 4th experiment here that was about optics, being able to actually see the thing that's out there. And so this is now a piece of debris that they put up there. They didn't go after somebody else's, this is their own stuff. So they put a piece of debris up there, and then they fired the net, and as you can imagine, what happens if you fire a net at something? It's going to start tumbling down, and eventually it's going to deorbit, okay? So again, from a civilian's perspective, this is really cool stuff, the fact that they can actually do this. All right, because this is what we've been needing for a long time. This is slow motion. It's kind of like Spider-Man, right? And it's a tumbling piece of debris. It catches it, and then it just tumbles down. But basically, and again, another book. It's up to us to teach, whether it's our children or whether it's future generations of individuals that work in space, that are going to live in space. This is a serious issue. This is a problem, and we need to be smart about how we work, smart about how we play in space, so that future generations, just like here on Earth, I could be talking about an oil spill here on Earth. It's the exact same pitch. We got to protect our environment so that future generations can enjoy it and live and work and do whatever else they need to do in there. And I'd like to close with this commercial. It's not really a commercial, but it is a commercial, but it's not intended as a commercial, okay? So, and hopefully you'll hear the sound, because there was some cool stuff here.
Sir, debris headed towards our comm satellite. Impact may cut off communications with ground forces. Launch avoidance maneuver. 20 kilometers in closing.
What's going to happen?
Collision averted, sir.
This is the best part. It's not science fiction.
All updates are accounted for.
It's what we do every day. You guys can relate to this, right? It's not science fiction. It's what you all do every day. I thought that was a really cool tagline. But anyway, so. And with that, I'll close.